So firstly, let me recap the discussion about explicit versus implicit finality. With explicit finality, essentially nodes detect that a block is safe or that something is safe, explicitly decide on it, and then will no longer kind of accept anything that contradicts that. So the fork choice rule will kind of be modified to take the already finalized stuff and only return things that are consistent with it. And that's kind of the explicit finality route. The implicit finality route is the route that kind of is taken in the specification that I wrote up, which is basically that like we define protocol states as sets of messages that exhibit less than some number of Byzantine faults. And so like as people make messages, our possibility to go into a protocol state where some block isn't included kind of disappears, because it's impossible for us to go to a superset of our current view that doesn't introduce more than some number of faults, but doesn't have that block in there. So in this strategy, we filter messages from being like looked at by the fork choice rule based on the Byzantine faults that are observed, as opposed to whether or not they agree with the finalized stuff, or whether or not they contradict the finalized stuff. So this is kind of in some way simpler and more elegant, but the downside that Dan Robinson identified is that we're going to ignore more messages. Like less messages are actually going to end up in our view if we don't allow messages come in and if they exhibit more than some number of faults, than if we have a kind of a strategy that allows more messages in, and therefore somehow is more inclusive. For example, if I have a message that in its dependency exhibits a bunch of faults, then like you might never see it, even though I was never Byzantine. But there are benefits to implicit finality. For example, like you are as good as the ideal oracle in some way, right? Like your decisions happen implicitly as soon as the ideal oracle will fail to attack. There's no question about being sure to decide on enough things. So you could imagine that the task of deciding on everything that is safe could be quite more complicated than it is in a blockchain, where we only really need to ask about whether blocks are in the chain. And then in that kind of context, maybe implicit finality will be more scalable or feasible, because it will like finalize stuff that you haven't bothered yet to compute whether or not it's safe. So that discussion was quite interesting. I didn't participate in it, till the end. So maybe Michael wants to jump in with any kind of takeaways.
No, I kind of felt like I jumped in near the end, because I think a lot of that discussion was happening, I guess 2 weeks ago over the weekend, and then I sort of came in on Monday and saw tons of messages, and tried to read through and sort of jump in on that a little bit. But I think mostly what we concluded was that, I mean, I think it was, I didn't quite understand why the discussion started to begin with, but it was about maintaining finality in the presence of greater than your fault tolerance number of Byzantine faults. Right. So, yeah, and then, yeah. So, and so you're saying that we either ignore those messages so that we never actually exceed our fault threshold, or we have some extra inputs into the fork choice rule that basically says these things can never be changed, and you can never choose things that contradict with these things.
Exactly. That's really well summarized. Yeah.
And so the only thing that sort of stood out to me from that was adding inputs to the estimator could make things weird. In that, if I'm a Byzantine node, maybe 1 minute I'm saying this set of blocks is finalized, and then the next minute I'm saying some other set of blocks is finalized, and I'm not sure if.
So Nate and I worked out a minimum constraint on that, which is namely like once anything gets added to your set of finalized things or your whatever accumulator of finalized things, it has to have been in the 4-choice rule of your last message. So it's not quite willy-nilly. We do have like some monotonicity.
But if I'm a Byzantine node, I can do whatever I want, right?
Well, no, you can equivocate or you can make an invalid message.
You can equivocate or you can make an invalid message, right? So, okay, I see what you're saying. So you're saying that other nodes would see that I must be changing my finalized stuff to make a particular sequence of messages, and that would count as invalid, and so it'd be ignored.
If you add anything to your set of finalized stuff that wasn't in your last messages estimate or like consistent with last message estimate, then that's invalid.
Okay, that makes sense.
So do you have any opinions about which way to go?
I guess I see both sides of the argument. Like I appreciate the sort of explicit finality from I don't know, I guess a perspective of explicit. I do tend to prefer, if only because it makes it clear to everyone without having to redo computations over and over again, right? If it's implicit, then other people have to recompute what my final decisions were. But I also I agree that the implicit way is far more elegant and nice, even if it does limit your view. And I also don't necessarily like limiting the view. I don't know. I'm torn.
So with the last finalized thing, you mean that it's like it might be more difficult to simulate in like a adversary model a node that hasn't finalized anything?
Sorry, you cut out for me there. Could you say that again?
I'm wondering what you mean by the extra computation.
So if something is explicitly finalized, shouldn't that mean that I can at a glance see what was finalized for someone? Like it's included, not just as an input to the estimator, but probably somewhere in the block as well. Like this is what I put into my estimator as being final.
Yeah, so you could see that in their blocks. Yeah.
Yeah. So what I mean is, just by looking at a single block, it's finalized for that validator, as opposed to having to look at a sequence of messages and deducing what's finalized using the implicit rules.
Well, I mean, you mean like looking at their view and running a safety oracle?
Yeah.
Yeah, but that's it's you kind of yeah. I mean, I see that somewhat, but I'm not sure why you ever need that information. Well, the question is basically whether the safety oracle will be more performant in the context of this information or not.
Yeah, maybe it's not overly relevant, and sort of comes down to the difference between elegance and inclusivity is maybe the main two things.
Yeah, it's an interesting conversation, and I think I would love to find a reason to go one way or the other, or to find the middle ground where we don't have to make a trade-off. Anyways, so I guess I could talk about sharding now, if everyone's down.
I'm down.
Okay, so I'm going to do some share screen here. Okay. So do you guys see this this page here of math?
Yep.
Yeah, sure do.
Cool. So basically, the way this process is going to work is, we're going to sit inside the correct by construction process and just define the message formats and for choice rules in order to basically give a sharding spec. And the idea is like, okay, we're going to have a similar safety type of properties where if something is safe on one shard, then that's going to mean that there isn't anything that implies that the negation of that thing on any of the other shards. And you know, we have very like the construction says nothing about actually which nodes validate which shards or anything like that, or like our proof doesn't force all of the nodes to have all opinions about all of the propositions, right? It's but it does give us a distributed safety kind of thing. So so basically what I'm going to define is a set of blocks, and then I'm going to define just a few if you give a few more definitions, and then we'll kind of call it a day for now. But because you know, I'm not really done writing everything up. So the blocks in a sharded blockchain basically there's two types of blocks. There's kind of normal blocks on shards, and then there's blocks that are called join blocks. Do you guys see my mouse, by the way?
Yeah, Vlad, is a product more binding than some?
So
How do you parenthesize that up that first equation?
basically it's a whole, it's basically a whole, like a choice between a bunch of products, really. I mean, because this is itself a product.
So it's open paren D cross B X close paren plus open paren sum.
Yeah.
Okay.
Yeah. So
okay, cool.
yeah, my bad. So let's talk about the block structure. So a block is either going to be, and this is kind of a minimum representation, it's either going to be another block with some data. So it's like data, like block data, and then a pointer to another block, essentially. But we're just going to represent it by just including that other block there. So a block on shard X is data and a block on shard X, or it's a merge block for some set here that includes X, or it's the genesis block of shard X. So basically there's three types of blocks on a shard. There's like the genesis block, there's the a block with just data and another block on that shard, and then there's this merge block, which is a block that basically merges that shard X with some other set of shards. And the merge blocks basically look kind of like this. They're identified by a set of shard identifiers, and they are data and then a block from each one of the shards. So basically, a merge block has a bunch of transactions or whatever is in the data, and then like a pointer to a block from every shard that is identified by that it merges, right? So like a block that merges shards x1, x2, and x3 will have some block data, and then a set of blocks, one from x1, one from shard x2, and one from shard x3. And then the set of all blocks basically is like, all of the blocks on all the shards, and then all the merge blocks across all the shards. That's kind of the block structure. And you can kind of follow any block to the genesis block, any block from a shard down to the genesis block by either going to the block with the data, or going to, you know, the block here from the same shard.
Are there any constraints on those blocks from other shards? Hi, this is Rick.
Hey, Rick. No, I mean, they're just blocks, and they're either blocks themselves or data in a block, or the genesis block, or a merge block.
Okay.
Hey, Rick.
Hey.
So this set function is pretty okay. It kind of chooses a member from each of these guys and makes a set out of them. And in this case, it talks about all of the sets that we compose in this way. So I'm not going to go spend too much time on the definition of set there. So the fork choice rule takes a set of blocks and returns a block on every shard. I'm not sure why this is a Z here. This should have been an S for the shard names. It's kind of a mistake there. And then these are the neat definitions. These are the definitions that we can maybe strive to satisfy with different sharding protocols in order to guarantee cross-shard atomicity. So then we're going to focus on the first one first. It basically says that, okay, well, for any block that's a merged block across shards x1 through xn, it's in the fork choice rules. So for any view, right? So for any view, which is like any set of blocks, the fork choice rules, choice of shards, choice of fork for shard x1 contains shard block B, which is this merge block that merges shard xi, if and only if the fork choice rule for shard xj also includes the merge block. So the idea is that the block is in each of the shards fork choice rules, or none of them, by the definition of the fork choice rule. And this is kind of the most kind of upfront way that we can get atomicity, by basically we're having fork choice rules that give us the property that a block is in their fork choice only, if and only if it's also in the fork choice rules of all the other shards that it merges. And then we have we can have this condition, which is quite a bit weaker, that says that it's not blocks that are atomic, but safe blocks that are atomic. So if a block is safe on shard xi, and it merges shard xi with xj, that it's also going to be safe on shard xj, and vice versa. Similarly, if it's safely not on shard xi, then it's going to be safely not on shard xj. So this is kind of a fork choice rule atomicity of the safety of merge blocks. So it's a weaker notion, which means that actually we can have possibly more scalability, because it's more of an eventual kind of property rather than an upfront property, the fork choice rule for all views. And then this is the kind of more interesting one, which is really the eventual. It's kind of an eventual atomicity of safe merge blocks. So it's not that like a block, if B is safe on xi, then B will necessarily also be safe on xj. Just that B, the exclusion of B will not be safe. It will definitely not be safe on xj. So like any options that exclude B are not going to be safe. So B will kind of either it'll be kind of bivalent forever, or B will get in there. And similarly, if the exclusion of B is safe on shard xi, then the inclusion of B on shard xj will not be safe, for any shard that's merged in block B. So this is the weakest definition of atomicity that I was able to come up with, and it kind of represents, I think, unless we find something weaker, maybe like a kind of ideal minimum that we can do to guarantee the atomicity of cross-shard blocks. I'm not necessarily sure if guaranteeing the atomicity of merged blocks is the best strategy. However, it's nice and simple because it acts on the block structure rather than on the transaction level. Any questions, thoughts?
So I like all of this. I think the last definition there is super interesting for sure and makes sense. Last week I had a meeting with some of the Pyrofex guys, and they were talking about our chain's namespace structure and sort of ideas for that, which is sharding for our chain, more or less. So maybe, I don't know if this is the right venue for it, but maybe we should chat at some point, or maybe I'll just go away with this and see if I can try to fit in the namespace model that they've come up with into these definitions and sort of see what it looks like.
Yeah. So basically, what I kind of have is in this description, the names are just a bunch of atoms in a set. However, like when I'm like continuing my sharding spec, I'm going to end up using binary strings, and I'm only going to let merge blocks exist between blocks that like agree between shards that have the same binary string except for kind of the last character. In this way, where like basically they're exactly the same except for one of them is one character longer.
Yeah.
And then they can have merge blocks. So I think the structure of names is gonna come up, but these definitions here I deliberately gave in terms of a set of names, so that I could give them in a more concise way.
Yeah, the name structure is going to ultimately mirror the structure of the blocks that you've given. That's what will emerge. There'll be a homomorphism between the names and the domain equation you've given for your blocks.
Interesting. Yeah. So right now, what I'm planning on doing is basically like constructing the fork choice rule to just like reject all the merge blocks that like I'm disallowing.
Yeah.
But yeah, I think that definitely the way that I'm talking about which merge blocks I'm allowing or not is in terms of the structure of the names, and I don't know if that's natural, but I started doing that for some reason.
Yeah. Actually, I started to think about it. I think there's a way to build a higher level calculus with a COM rule that is your fork choice rule. But essentially, your fork choice rule is deciding what things interact, which is effectively a kind of a coarser COM rule than the COM rule that we've got. So that's kind of interesting.
So in kind of right now, and most abstractly, the way I think about the fork choice rule is this like thing that maps the protocol states to like propositions about the consensus, right?
Mm-hmm.
And if the consensus is on, say, a bunch of communicating processes, then I feel like what you're saying kind of makes sense. But if it's on a bit, I don't know. I mean, I don't know if that's how that really works.
Well, think about the agents that are agreeing on the bit, that they all have behavior,
Mm-hmm.
right? So those are your processes. So it's the agents that are achieving consensus. Those are the things that are your processes, and then the COM rule has to do with how those agents interact.
Yeah, but the fork choice rule takes a bunch of messages that like from those agents and like returns a bit.
Yeah. So that's precisely the point. What it's doing is it's saying what are consistent continuations out of the existing state, which is what the COM rule does.
Well, what's it? What would be an inconsistent? I mean, we just have like a bits, right? Like 0 or 1. There's no real inconsistent set of possible values.
An inconsistent possible value would be the set 0 and 1.
Okay, I mean, if you allow that.
Right, exactly. Or if you don't allow that, then it's inconsistent.
What do you mean?
What I'm saying is that the agents are not allowed to get into certain states. So a state would be that they have the set of outcomes, right? And that's because you're disallowing that. So it would be inconsistent to be in that state.
Okay, well, sure. Yeah, I mean, but by not allowing, I just meant like assume won't happen. But I guess I hear you.
Yeah.
Okay. Anyways, I guess I'm done my part of the update unless anyone has any more questions about the sharding stuff. Cool. Well, I'm gonna stop screen sharing then, I guess.
Any other updates?
I guess I could go next and talk, I guess, briefly about what we talked about with our chain namespaces, get feedback on that from you guys. Basically, the idea is that we set up sort of a tree type hierarchy of namespaces. And the analogy that kept coming up was the idea of a file structure where you've got directories and subdirectories. And so at every level, it is itself still a namespace, right? No matter how deep into your file tree you go, you're still in a directory.
Yep.
But there could just be more namespaces below you.
Yep.
And the idea is that when two namespaces want to talk to each other, what they do is they push up their transactions to the nearest part of this file structure tree where they join up, and then the transaction happens there. So you get the atomicity from the fact that transactions only ever happen in one namespace. So they either happen in that namespace or they don't. But it's a question of which namespace that occurs in relative to where the source namespaces are. So doing a transaction in your own namespace is really quick and really easy, but doing a cross namespace one requires sort of pushing up to some top level and having it happen there.
Yeah, I mean, I think that's a serviceable set of intuitions. It's not the way I think about it, right? I think about namespaces as more like a data structure, and then validators are simply saying what namespaces they serve. So I don't think of the namespaces as having a lot of agency. So we don't talk about pushing up or something like doing something in your own namespace, but rather that in order for a transaction to happen, there have to be some validators that are servicing the namespaces that are touched by those transactions.
But this was exactly the point of reframing it this way, is that you sort of get around that problem of needing to have basically some validators touching every possible overlap, is that by sort of enforcing a tree structure, you guarantee that any two transactions will eventually occur. It might just take some time because it might have to travel up the tree a long distance.
Yeah,
without having to introduce any new validators that cover some new overlap.
Yeah, yeah. Go ahead.
That's not quite what he meant. I mean, I think that yes, there's going to be some like single validators that see the whole tree, probably just as a practical matter. But there'll be some union of validators that will be able to pathfind whether it's a tree structure. I mean, a tree structure is a good way to do pathfinding, but to discover those routes. But it sounds to me more like a validator sees a transaction, sees it crossing multiple namespaces, and needs to figure out a route to actually resolve or complete the transaction.
Yes. Exactly. It's much more dynamic, and you also want it to be market driven, right? Because you don't want to have you don't want to pre-impose this discipline.
Well, so as far as being market driven goes, the tree can be restructured. That was the other piece of it, is that just like in a file system, how you can move directories around, if it's the case that everyone in one namespace decides, oh, we need to be talking to this other namespace constantly, let's either move closer together in the tree or merge together into one namespace. That kind of reorganization can happen. So you have the market-driven stuff going on in that sense. This was all motivated by Mike Stay's observation that you already kind of have this notion in the row calculus with the idea of scope extrusion, right? You've got your new operator defining a scope, and if a variable is free, in the other process, you can move it in and out of that scope, which was the idea of being able to move something, like if you have a nested group of new type structures, your nested scopes, then by creating a new process that isn't bound by the scope you're in, you can move up, basically was the idea.
No, this is all already yeah. If you want to look at an analysis of the minimality of the tree structure, Milner has a nice paper called Naming Monoids. So these are monoids that provide a notion of name, and it's one of the 3 principal control structure papers. It's a little hard to find these days, but I'm pretty sure I have a copy floating around. So if you want a copy, and basically what he's saying is that once names have structure, in order to be consistent, they have to be monoids of a particular type, and the sort of minimal representation structure, you know, in the same way that there's a representation theorem, and the representation theorem is that all the monoids that have this characterization end up being a kind of tree structure, which is exactly what you're discovering now.
I would love to read this paper for sure. Yeah, so if you have a copy,
yeah,
feel free to send it.
Yeah, I'll make it available. Sure.
Vitalik and I had a conversation about like what it would take to like satisfy the like kind of atomicity thing, and he kind of boiled it down to like there's like a SAT problem, because you know different merge blocks could potentially conflict, and you can't necessarily have 2 merge blocks be both allowed. And in the end, you know, we didn't really like go down that route too much, because they're like in this situation in like with the tree structure for the sharding, it ended up being like easy to kind of only allow merge blocks between nodes that are adjacent in the tree, and that kind of like led to us like somehow automatically solving the SAT problem rather than having to do a bunch of computation to in the 4 choice rule.
Yeah, that smells right. Yeah, it has. Yeah, that's similar to the kind of thing that I was doing with the logic for blocks thing.
The other thing that Nash pointed out about this is that it sort of also yields a nice reflection of how the hardware itself will be structured, right? These nodes serving messages near the top of the tree will likely need to be basically full nodes with like some good hardware to handle the volume of messages going through there. Whereas if me and my buddies want to start up a little namespace down near the bottom of the tree with like our bootleg hardware, that's fine. Doesn't impact anyone else, right?
Mm-hmm.
And then the other thing that I was thinking about last week, and Greg and I were having sort of an asynchronous discussion about it over Discord, was the idea of overhead in consensus protocols in general if one of the inputs to your consensus protocol itself requires consensus. And I also brought this up on the Casper Discord, and Dan very kindly had a discussion with me about it. So in the end, what I took away from the conversation was, yes, there is overhead if you have something in your consensus protocol that itself requires consensus, but as long as that thing isn't changing super frequently, it's probably fine.
Yeah.
Was that the takeaway that other people had as well?
I wasn't on the conversation. I was in Costa Rica, so I don't know.
Well, okay, so I guess we'll.
Well, yeah, we
Basically,
should.
the reason that I was bringing this up is because when I was looking at political capital is changing constantly. And if it's a thing that we need, like if it's a thing that we need to conserve, which I think at this point we're all in agreement that you would need to conserve it, then you basically need a ledger for it. And now you have some other thing that you're trying to keep consensus on. And that does constantly change because political capital balances are constantly shifting. And so I'm not sure if the overhead there is reasonable at that point. I suppose I could try to do some kind of experimental, like write up a simulation and sort of see if I can derive what the overhead might be. But I am unsure if that's worth the effort required.
Well, actually, I have a lot more motivation. I finally got to the meat of the book in the Honeybee Democracy, where he does the analysis, he does the comparison between the data on eye movement in primates and sort of brain structure, and compares that to the next site for the hive in swarm decision making. And he has a really nice model for the decision-making processes. These are essentially decentralized consensus processes, but they're very, very practical and very well tested. And so they have a very, very nice deep learning model, essentially, that requires the kind of mutual inhibition structure that the political capital is designed to provide. And so whether or not the political capital is the right answer, there's a constraint that I knew I was intuiting that for which there's a very, very clear experimental data in support of. So I'm hoping to give an update on that next week. I didn't put together all the. I wanted to put some slides together to summarize this stuff, so people don't have to read Honeybee Democracy. It's a great read. It's a fantastic read, but you can kind of boil down the relevant stuff to just a couple of pages. So to me, the thing that's really important here is that these are distributed, decentralized decision-making processes in the wild that have been beaten on by actual evolution for a very long time. So and there's some very nice models with some nice parameter tuning, where you tune the parameters, you get different decision-making qualities. So that's why I think that they're relevant.
So what I'm hearing from you, Greg, is that you would like me to write up a simulation that does the political capital ledger and try to quantify the overhead that it incurs?
Not necessarily. I think what I want to do is I want to hone in on what I'm trying to. Like, the political capital was just a mechanism for getting at a way of expressing certain constraints that I think have to be on the process. I don't know if it's the only mechanism. I don't have a proof that that's the mechanism, but the constraints, I think, are really quite important. There's a mutual inhibitory constraint, and then there's this validator randomization constraint. And when you put the two together, the political capital was just my tiny brain's way of solving that constraint system in one go. There might be other solutions, but now I think I have a way to state the constraints more abstractly, and then we can look for better ways to implement it that maybe don't require so much overhead in the consensus.
I posted about this in the Casper Discord. Has anyone looked at Byteball before? It's another cryptocurrency.
I've heard of it. I haven't had a chance to go down the rabbit hole.
I looked at it. Byteball.
So I read their paper on sort of how they do the consensus, and I just sort of noted that it has a lot of similarities with Casper in terms of sort of its overall setup. With like the one major difference being that their validators are chosen for external reasons, not for staking. But I think it's interesting and kind of cool. So I don't know. I would encourage others to look at it and maybe let me know, or we can talk about it at some point. But I think going along with what you're talking about, Greg, there is this notion of sort of constraints and swarm decision making that you're talking about. It doesn't do validator randomization because the validators are externally chosen. But maybe we could find a way to modify sort of what they're doing in order to include that.
Cool. I'll take a look. Does anyone mind if I go next? We have 10 minutes left in the process.
Yeah, please go ahead.
Cool. Just grabbing a screen share. There we go. Is this large enough type that everyone can see it? I tried to fit it in one page.
Yep.
It's large, yep.
Okay, cool. All right, I think I can go to slideshow view. Okay, there we go. All right, so the idea, which I spotted while I was driving from Seattle to Vancouver, Canada, one very snowy evening in 2008, was to build a variant of the row calculus in which locations in the sense of the zipper are names. And the rationale for that is that we then get all the features of the ambient calculus where you can where you have a notion of physical location of a process that can be correlated to fault tolerance and other kinds of things and security, at the same time as having sort of the more pi calculusy kind of approach. So you can talk about processes moving around in a tree-like structure. So not unlike moving around in a sharded structure. It also has some other applications, where I'm beginning to get geometry to emerge out of the behavioral characteristics of processes, but I won't touch on those in this discussion. So basically, it's very similar to things that we've talked about before. So processes are either the stopped process, or you've got input guarded continuations and output and parallel composition, and then here you have the usual dereferencing of names, which are quoted processes or something like quoted processes. Looks like it's a little bit off, but there are two new pieces. One is a situation catalyst. Here, what I'm doing is I'm taking the idea that Mike Stay and I developed a few years ago, where in order to model the pi calculus categorically, we needed the notion of a catalyst in order to prevent execution under a prefix. So here our models were failing because P could go ahead and go forward without the guard having been satisfied. And so I had this flash of an idea. What if we say that there's a special element called com, a special morphism called com, which represented the com rule, and that had to be present in order for there to be any interaction. And here I'm taking that idea a step further, and I'm making com catalysts be first-class processes rather than rules on the side. And there's a similar kind of thing over here where there's another kind of catalyst which is related to how comms are formed. And this has to do with being able to update a location. And now the notion of a location is really quite straightforward. It's just exactly what we expect. So there's a context and a process. So if you look at Uwe's zipper idea, that's exactly the notion of location in the zipper. And here what we're saying is that such pairs are what constitute names. And if you were to, and this is not very far from the row calculus said a quoted process is a name. If you stuff a process inside a context, you get back a process. So it's basically just decomposing the process at a particular point. It's splitting the process into the surrounding context and the process that goes into that context. And the place where it goes in is the location. So that's what's going on here. And then I have to tell you what a context is. Well, a context is either a hole where you plug a process, or it's an input guarded context, or it's an output context, or it's a parallel context, and that's it, nothing else. And then now you have this idea of two different interaction rules, and you update the. Sorry, I was in the middle of typing this while we were talking, and I didn't quite finish typing this one thing. I'll type that in right now. Okay, so the idea is that in the presence of a com catalyst, output and input can meet at the same location, and then you move forward where the communication event has happened. But you don't get to just do the quoted Q thing. You have to take the K here from the com catalyst, and then you'll get the substitution. Right, so you actually need this context in order to form a name. And so essentially what's going to happen, just jumping ahead, if we ever encounter a star where we're doing a substitution, then we're going to start running that queue, but in that context. So this is a surrounding context. And one way to think about this intuitively is imagine that you've got processes that are communicating across different layers of the network. So you've got a process that's communicating way up at the HTTPS level, and you've got another process that's communicating way down at the TCP level, right? And in order for them to communicate, you have to have this adapter, right, which will either unpack things that are framed with HTTP framing, or repackage things which are just TCP framed back all the way up to HTTP framed stuff. And so this K, this context, in one direction is going to be the unframing, the unpacking, and in another direction it will be the repacking, right? So that's what you can think of Ks as like adapters. Another example would be in physical systems, where what's happening in the nucleus of the cell is happening, kind of in the, sub-second time frame, but not like, lightning fast, like near instantaneous. Whereas what's happening in the cytoplasm is happening, like in the femtosecond range. I mean, that's a bit of an exaggeration, but you get the idea. It's crossed, several orders of magnitude of temporal scale. Right, and so and the reason I mention this is because it's quite practical. I mean, like cells really do this. In the wild, cells will be impinged by all kinds of environmental stuff, and the cytoplasm around the nucleus is reacting in lightning fast, and then passing information onto the nucleus, which is taking its good sweet time to produce proteins that might impact the cell's response to the stimulus that impinged on the membrane of the cell. So these Ks are mediating. You can think of these Ks as mediating that temporal scale as well. So then the final piece of the puzzle is that sometimes you want to be able to update a location site, and so what this does is it evaporates the queue, it erases the queue and turns it back into one of these COM catalysts where we've kept the context around. And so now I'll just do one very, very quick on the fly calculation, just to give people a flavor of what computation in a calculus like this looks like. I'll just get rid of this and that. That's all gone. And then I'm going to get rid of that and that, and then just do this one. Okay, that should be big enough to read. Okay, so now what we want is, well, what's, just for grins, does anyone know what the first name looks like? So just staring at this for a second.
I put my guess in the chat.
That's exactly it. That's correct. Yep. That's our first name. And so now let's build like one of the simplest processes we can out of this. So I'm going to do a for, and here I'm going to use just some name. Coming from that first name. And then all I'm going to do is to start running whatever we get. And so then I'm going to take that and I'm going to run that with output on the first name. And here I'm just going to make this parametric in P. And then I'm going to run that in parallel with some COM K prime. And we can see that this is going to go directly to the star at K comma Q, right? And that's going to be, we're going to run that with the substitution at K prime comma P for at KQ. And then if we look at our substitution rule, right, that's going to be equal to K prime comma P. So what we've done is we've dropped K, we've dropped P down into K prime, just so that, and the, here, let me just do a quick, so we can get it all in there. So that's the calculation. And what that does is it shows that we can transport, and now if you were to take K prime to be a context that was roughly like this one, so basically a structure like this with a P inside it and maybe some junk left over, then we can shuffle P over into a K double prime and P over into a K triple prime and so on. And so you can now describe the motion of P's. If you think now of processes as objects, you can now see that they can travel in space, where the space is described by contexts. So that's how you can begin to develop a notion of geometry that emerges from the behavior. And this is very different than the Cardelli and Gardner idea of instantiating processes where the names are vectors in a vector space. Here we're not starting with the notion of geometry and kind of adding process behavior to it. Rather, the notion of geometry emerges from the process idea. Anyway, so that's that gives us that's the rough idea of the calculus, and you can see how to calculate with it, and more later.
That's just awesome, Greg. I just never cease to amaze me.
Well, this is good fun. I was really happy. I honestly have been trying to write this calculus down for about 10 years. And so I feel pretty like a slow camper. Any other comments or thoughts?
Where I kind of get a little bit lost is relating the process geometry to physical geometry.
Yeah, I purposefully didn't write that down because or in this discussion, because it would take us a long time. I have to build up a bunch of machinery in order to talk about what the metric. There's a we can define a metric here, and then we can talk about the distance between two processes, and we say two processes are co-located if they have the potential to interact inside a context, and they're distant if there has to be some evaluation before they get to interact. And all of that requires, like, since processes can wiggle, right, you have to talk about, their stability while they're moving around before they get to interact. So it ends up being, quite a subtle idea.
How is this distinct from quantum logical processing?
Oh, we don't have any assumptions about linearity in the same way. So the quantum stuff is all linear, right? It's all reversible. Here it's clearly not reversible. That these two rules forget stuff. And you could build a reversible notion of computing on top of this, or you could build a notion of reversible computing, or you could potentially encode this in a reversible situation. So
well, yeah, okay. I guess the distinction is this describes what happens that is not reversible.
Yeah, something like that. Yeah. Cool. Well, I know we're over. Sorry, it took longer than I thought. Do we have any other updates? Sweet. So I guess we can see everyone next week.
Yep, sounds good. Sounds good.
Hey, Vlad, do you want to coordinate about possibly visiting Aalborg and Aarhus? Oops.